So when we're looking at NMR, what we're talking about is nuclear spins, okay? In particular, nuclear magnetic moments. NM, nuclear magnetic, that's what we're referencing. And now it's a resonance. That resonance is its alignment with a larger magnetic field. Okay? So if we take a really simple atom, just drop a hydrogen inside a nucleus or inside a magnet, that hydrogen has the potential to either align with the field or against the field. Okay? If I bond something to that hydrogen, that is now going to affect that spin state. Okay? I can see that effect when I knock either of those spin states off axis, and I knock them off using radio frequencies. So I fire radio waves at my sample. That hydrogen spin state, so let's, whoa. So radio waves. And now that moment is now messed up. It doesn't align with the external magnet. Okay? We can detect that disruption in the magnetic field, and we can time how long it takes for that to realign to the external magnet. Okay? That timing process, spin states, what radio frequencies we used, all gets factored in to generate the NMR spectrum. Okay? So each of the pieces of information we get from NMR have some aspect to do back with this magnetic moment of our nucleus and how long or short or quickly it takes to realign with the field. Okay? So if we think just about that timeline, that's what's referencing the immediate local environment. Okay? What is next to that hydrogen? Okay? How does that change things? Well, that other atom brings in electrons. Those electrons can distribute around the hydrogen, which then means it's harder for that internal nucleus to see the larger magnetic field. So electrons will hide or shield our nuclei. So depending on what our hydrogen is connected to, right, it takes longer or different energy radio waves, right, and different times to realign with the field. We correlate that to a particular atom type, okay, or bond type, be it hydrogen bonded to carbon or hydrogen bonded to oxygen, etc. Okay? So the more electrons around it, the more the nuclei is shielded. So what happens if I compare, say, carbon to hydrogen versus oxygen to hydrogen? What is the difference between those? Oxygen being more electronegative is going to withdraw electrons away from the hydrogen, which means its shield has been removed, which means it changes where it shows up in our NMR spectrum. Okay? So we can refer to that shielding as either shielded or de-shielded. Shielded means it's near a bunch of electrons. De-shielded means the electrons have been removed. And that causes our signal to slide around. That's what's known as our chemical shift. Okay? So what we're thinking about or referencing is just the spin state of those nuclei. Okay? Here's a nice little picture, real simple. You take a big magnet, you got a magnet controller, you drop your sample in, which detects what's happening within the internal magnets. An RF transmitter, RF for radio frequency, and it spits it out as some data. We get some peaks, kind of like most systems. So it looks relatively straightforward and simple until we actually look at a bit of scale. That thing that says 850, that's the NMR. The sample that goes into that NMR is about the size of my pen. Okay? So you're dropping a very tiny sample into that. What does that 850 represent? It's how big the magnet is. Okay? That's a really big magnet. Okay? That's why you need stairs to get up on top of it. Okay? Kind of the default magnet now is a 400 megahertz magnet, so about half the size of that as far as the magnet field goes. The 400 megahertz, you still have to get on stairs. I think the sample is about, 7 feet up? Is where you have to put the sample in. The magnet itself, I'm probably doing rough justice to the size of it. Okay, so it's pretty big. Okay. 10 years ago, the default was 300. Okay, why did it jump up to 400? We have technology to get better magnets, okay, and bigger magnets. Okay. ASU, so this is in megahertz, I think. Could be wrong. What's after mega? What's the next one? After nobody knows. I was going to say giga. Is it giga? ASU, I think, has up to a gigabyte. Not gigabyte, a gigahertz magnet. Okay, so their magnet is even larger, okay, and taller. Okay, why would we need bigger and bigger magnets? Well, what those magnets do is help us resolve the individual signals. Okay, so when you looked at the NMR spectra, because you've been looking at them, okay, you see peaks. Okay? The distance between those peak values will never change from instrument to instrument. Right? Because that would suck if they did, right? Because then you can't say, well, I expect an alkane to show up in the 0 to 2 range. I'd have to be like, well, I expect an alkane to show up in the 0 to 2 on a 300 megahertz instrument. If I make it a 500 megahertz, now it's 0 to 3.5. Right? That would not be cool. Right? But what does change when we scale up in the size of that external magnet is the width of the peaks. Okay? It's effectively the resolution. Like you get 1 megapixel cameras. Anybody remember those? Does that even exist? Okay. We're now way, way higher than that because the technology allows us to do that. A 1 megapixel camera was pretty cool. You got decent pictures. You could print that out and it wasn't too bad. Okay. But what happens if you wanted to zoom in on that picture? It gets very pixelated. The same thing is happening with NMR. So we can zoom in on spectra off of an 850 megahertz magnet to get very precise pinpoint precision in those values. Okay? We get very, very detailed information. The exact values themselves don't change from instrument to instrument. Kind of makes sense? Okay. There are all sorts of formulas and calculations you can run, which I believe the textbook shows you in the first section on NMR. You are welcome to play with those numbers if you would like to. I don't even think I asked questions in the smart work about it because it's just, I don't see the value added. Okay? So what you should realize is the individual chemical shift values won't change. Okay? Other things, when we're looking at the experiment itself, oh, actually, this is just a random fun story. Some of the spectra that you will see throughout the year or even next semester came from me actually running, I think, 70 different compounds through these spectra so that we had real spectra to give students. So that was kind of a fun project, so which meant I lived in the NMR facility at ASU for the summer. I should probably pause that. So experimental considerations. Okay, more or less shielded or deshielded than what? Okay, so the whole point is it just says that this is more shielded. There's more electrons around it than what? Okay, you need a numerical scale on that. And all the instrument spits out, it says it's just way on the right or it's way on the left. There's no numbers associated with it. So this is why we had to use a standard. That standard gets inserted into the samples and is always tested. Okay? That standard is TMS, okay? Tetramethylsilane. Okay? That signal is defined as 0. So that's as shielded as it gets. Okay? So everything else will show up more deshielded than that. Okay? Why is this important to reference? Depending on the spectra you look at, you will see a peak at 0. Why? That's the standard. You needed it. Okay? So that's why it shows up. Okay? So organic protons should absorb more deshielded than that. As I said in the videos, I get shielding and deshielding backwards all the time. As I try to not screw it up. Deshielded is downfield, which is bigger numbers, which for whatever freaking reason is to the left. Right. You know, just for that, I'm just going to skip the next 10 slides. Okay. One of the things that also, I was kidding about that. One of the other things that has to happen within our samples is that they have to tumble and move. Why do they have to tumble and move? It's detecting the local environment of a hydrogen. Okay. Which means if the molecule is locked in space, a hydrogen aimed up, even if it's connected to the same carbon, a different carbon where that hydrogen is aimed down are now different. And we would see multiple signals. So what we have to allow for is the molecules to freely rotate and move so that we minimize that confusion in our spectra. Okay? So they always have to go in liquid form. This becomes a problem because what about the organic substances that you've worked with in lab today or in the past? Are they all liquids? We get a lot of solids. Okay? So how do we fix that? We have to make a solution. Okay? That solution that we use is typically chloroform because chloroform has a pretty good solubility for most organic substances and it dissolves almost all of them. Another common one is dimethyl sulfoxide. You'll sometimes also see water show up. The problem with all three of those, they all have hydrogen in them. Okay? And for that matter, carbon. Why does that become problematic? That shows up in your spectra. Okay? And because it's the solvent, the concentration of the solvent is massive. The amount of compound you put in is very small in comparison to it, which means I see a massive signal for the solvent that probably overwhelms the ability to see anything else. Okay? So that becomes an issue with those solvents. So what do we do? As per the video, you deuterate them. Deuterium is still hydrogen, okay, for the largest approximation that we're going to deal with, or the simplest approximation we deal with, except that it has an extra neutron. Guess what that neutron does? It nullifies the magnetic moment of the hydrogen nucleus. Because it is no longer magnetic, it doesn't get detected by the instrument. Okay? So we end up deuterating our solvents. Okay? As someone asked about in the video, if it's deuterated and there's no hydrogen, then how come I still see a signal for it in my HNMR? And it's just HNMR. Well, as I talked about really quickly, that's due to hydrogen exchange. Okay? Hydrogen as an atom is everywhere, which means when we open up that container of chloroform, it gets exposed to water. Water comes into the reaction, and hydrogen will come on and off of water in exchange with the deuterium in that compound, which then means we get a little bit of hydrogen in our chloroform, which means we see it show up. Okay, why else might we see it show up? We're cheap, and we don't buy 100% deuterated chloroform. Okay, we buy 99%. Now we spend a fraction of the price, but we see that spectrum or that piece show up. The carbon NMR becomes less of an issue. We don't actually change that one around. Why do we not worry about it in the carbon NMR? Trying to find a new isotope. In carbon NMR, you're detecting already a very small percentage of carbon. The amount of carbon-13 in those solvents is low enough that it doesn't wipe out your signal. It'll show up, but it doesn't wipe out your signal. Kind of make sense? So if you're looking at the spectra packets, the ones that are lettered with letters, the ones that are lettered, there we go, okay? Those ones are real spectra. You should expect to see chloroform in those. And to that same extent, because they're real spectra, there are sometimes impurities that come along with it. The chloroform that we used was old. I think it had some water in it. Some of those compounds had water in it and impurities. Those signals also show up in the NMR. Dimethyl sulfoxide is extra challenging because there's 6 hydrogens in dimethyl sulfoxide, so it becomes D6, D for deuterium, and I'm replacing all 6 with deuterium for DMSO. Dimethyl sulfoxide. Cool? So there we go. Background. So what do we get out of it? 4 big things. Number of signals. This works for both hydrogen and carbon. Okay, the number of signals correspond to the number of unique hydrogens or carbons. Okay, that unique can become a challenging statement. That's why we did all of that rotational stuff and bonds and drawings and all that fun stuff in the first unit. Okay, looking at two different structures and saying, are they the same or are they different? We're doing that now at a molecular level to determine the number of signals. Right? So all you have to go through and do is count the number of signals that you see. That gets you your number of unique hydrogens or carbons. Since all you have to do is count, it's not that bad, right? Get a decent amount of information. You now know the number of hydrogens or carbons. Okay? The next one is chemical shift. This gets us our rough local environment. Okay? So when I take that hydrogen and I bond it next to a carbon, that's a slightly different chemical environment than bonded to an oxygen. That's my chemical shift. It gives me a ballpark idea of where my hydrogen is in the case of HNMR or my carbon is for carbon NMR. The next piece of information I can pull from it is our integration. All right, the big thing to be concerned about with integration is it gives you the ratio of unique hydrogens. Not the number, the ratio. Sometimes it is the number, because sometimes the ratio is the smallest possible and it matches your compound. Sometimes it doesn't. Okay, so be careful with that. Most real spectra spit out ratios that are stupidly high numbers. Okay, thousands. Why thousands? When we're talking about integration, the instrument is counting how many hydrogens were in that signal. So why thousands? When the instrument looked at the sample, how many hydrogens did it see? Thousands of hydrogens. So it's effectively a counting aspect of it. Every single hydrogen gets counted. If those hydrogens aren't unique, their chemical shifts place them in the exact same space, which means we see only one signal, but what happens to that signal? It gets bigger because there's more things getting placed at that point. Okay? So that's why we reference it as an integration, because it is literally an integration. It's the area underneath the curve. Those first three things aren't too horrible to deal with. So if you can nail down those first three things, you can actually answer probably 70-80% of spectroscopy questions. Okay, so that isn't bad. Okay, those first three things are also not for both carbon and hydrogen. Note, when we move to integration, it says hydrogen. It doesn't reference carbon. Why not? Because carbon gets a lot more complicated and we don't look at the integrations for carbon. Okay? This last one, our multiplicity, also known as splitting, okay, is exceptionally difficult. Okay? It also has tons more information. So when you talk to an experienced person studying NMR, the very first thing they do is look right to the splitting, because they can pull a lot of information out of it because they've internalized the first three. If you haven't figured out how to do the first three fast, don't look at splitting. Okay? This is not the time to do so. During spring break, go for it. Okay? Accept splitting as a point loss on the exam. Okay? Which I know sucks, but that's what you should do. Because if you try to figure out splitting and you don't know the first three, you're going to get splitting wrong, and you're going to get the top three wrong too. Does that make sense? Okay, so difficulty. Splitting is the most difficult. What information do we get? It's up there. What do you got, Miles?
I was saying the chart helps with.
So that organization chart that I asked you to go through and do if you're in the lab for, I think, 3 of 5 spectra, okay, drastically organizes this process so that you can glean that information and very logically stepwise through it. Okay, so we report chemical shift first. What does that mean? We report integration. What does that mean? We report multiplicity. What does that mean? What does that mean? So it forces you to go through those individual steps. Okay? So if you're doing those first, whatever it is, 4 columns, and you're doing those consistently right, cool. Now move on to the multiplicity. If you aren't doing those first 4 right, then don't move on to multiplicity. Okay? What does it give you? It gives you information about your number of hydrogens. Okay? And different here becomes a bit challenging, and we'll see that when we look at actual examples. Okay? So let's take a swing through first. Unique atoms, the easiest way to do it, take a molecule, build it, point to a hydrogen, close your eyes, spin, flip, rotate. Can you point to the exact same hydrogen again? If you can, that hydrogen is unique from all the other hydrogens. If you can't, it is the same as whatever hydrogen you're getting it confused with. Those together become one signal. Okay? That in and of itself isn't a big deal. That's relatively simple. Okay? But as we get more complex things coming out, we can come up with slight confusions that can make things a little more challenging. Your textbook reference names or relationships between those hydrogens. Okay? If they're homotopic, they're the same signal. If they're enantiotopic, same signal. Diastereotopic, you get unique signals. Okay? Those are cool, fancy words that I never bothered to learn until I had to teach. But, okay? So my recommendation is don't worry about the words. Worry about how you label your hydrogens. Okay? So should we take a look at an example? Those two are the exact same structure. And we'll see why I'm drawing two in a second. Okay? So let's just take a look at the left one. How many unique hydrogen signals do you expect to see? Okay? It might help if we had hydrogens on there, right?
It's 3, it's not 4, because the 2x.
Okay? So I've heard 3 and 4. You want the bad news? Both of those are wrong. Okay? So let's not stress about why it's wrong. Let's go to the simple level first. 4 is the most correct answer in this case. Okay? So why? Are the red ones different from the blue? Ignore the colors.
Yes.
Yes, why?
Because there's a carbon and carbon.
If we look at where they're connected, where the blue one's connected, it's connected to a carbon that's connected to a chlorine. The red ones are connected to a carbon that's connected to a carbon, right? Okay. How about the purple ones? Are they different from blue and red? So we could do the connect to a carbon, connect to the carbon game. We could also play the 3 hydrogens, 1 hydrogen, 2 hydrogen game, right? Okay, so that also helps to differentiate. Okay, and I heard 3, and I think I know why you were going with 3. We have 3 orange hydrogens, 3 red hydrogens. Are those the same?
Same? Well, no.
Okay, they're not the same. Yes, they're still 3 hydrogens connected to a carbon, but would you ever confuse the orange hydrogens with the red hydrogens?
No.
And you wouldn't, because look where they are with respect to that chlorine. The red hydrogens are 1 bond, depending on how you want to count, 2 bonds away from the chlorine. The orange ones are 3 bonds away. So that distance changes, which means red and orange are different from each other. So we should at least be jumping to 4 different carbons. Fudge. 4 different hydrogens, thank you. Are we good on that? Okay, because it definitely gets a whole lot worse. Okay? I just want to make sure we're okay with that. Yep, I forgot what it was. So it's not 4. It's 5. Okay, and some people have already been shouting out an answer, so if you started to shout out an answer, shut up. Why is it 5? Where's that 5th new hydrogen?
Somewhere.
It's somewhere, yeah. It's that black one. That black was a bad color. Let's try green. Is green better? Okay, there we go. The green one. The green and the purple are actually different.
Oh.
Okay? That is exceptionally difficult. So we're looking at the range of difficulty on this. Getting to 4, awesome. That's fantastic. I love it. Getting to 5 is a whole nother layer of just whatever you want to pile. Okay? If you like it, it's awesomeness. If you don't, it's not. Okay? Why is the green different from the purple?
Splitting.
This chiral center.
Because of that carbon. That carbon being a chiral atom is what messes with this whole system. Okay? That chlorine is wedged, which means when I get to this carbon, it's tetrahedral. I should be specifying wedges and dashes on that. So if we called that green one wedged and that purple one dashed, feel free to build out the model kit. You will find that you will be able to identify the green one versus the purple one every single time, as long as you really have a lock on chirality. Struggling with chirality, you're going to have a horrible time figuring that out. Okay? This is where that book is actually referencing this homotopic and antiotopic diastereotopic stuff. It is an attempt to help make this more apparent and obvious. Okay? Where it's being apparent and more obvious is this diastereotopic relationship. So what I'm going to do is take that green one and I'm going to say, I'm going to make it atom X. You're like, why? We'll see in a second. Atom X. Just to make it different from that purple hydrogen. I'm going to do the same thing on that other structure that I drew next door, right? Except now atom X is going to be purple one. And now everybody's favorite. What is the relationship between these two structures? They're diastereomers. What does that mean about those hydrogens? They are diastereotopic. They are unique hydrogens. You can be like, that sucks. It does. I agree with you. It doesn't change that it's still there. Okay? Why does that not mess with, say, the other one? You're like, but aren't there other atoms in there that could mess with this? Sure. So let's go through, do the same thing out here. Hydrogen, hydrogen, and we'll drop that in as an X. I'll stop soon. That probably means I'm just moving on to something else awful, but what is the relationship now between those? Those are enantiomers. Okay? That makes them enantiotopic when I did that exchange, which means same signal. Okay? So you could go through and do this breakdown for every single thing and try and piece it all together, and that would be great and fantastic, and the angels would sing. Okay? Ultimately, what you need to be able to do is count your hydrogens and realize that when you see a chiral atom, it exponentially got more difficult when trying to determine the number of signals. Okay? That chiral atom will also affect virtually every other piece of information you glean from the NMR. Okay? Yay! Okay? For those of you that have attempted the spectroscopy packet, how many of those had chiral atoms in them? 2. Okay? And they were labeled as hard ones, which means rip them up, that works. You could just rip them up and ignore those ones and not stress about them. If you really want to drive into the material, then that's where you need to dig into and actually see it. Okay? And that's where you have to evaluate that deeper level. Okay? Yes?
Can like a methyl group be diastereotopic?
The methyl group won't be diastereotopic, and why?
Because everything changes.
So with the sun, not whether.
2 groups always come out as the same thing because of their hydrogens.
Oh, I see.
Okay? And that's what changes it. That's why when we move to the methyl group, we don't stress about it. Okay? So, the next fun thing that comes out of this, okay, because it's always fun, right? If I say fun enough, you start to like it. When we looked at this, I'm going to do this, oh well. So when I look at this, there are 5 unique hydrogens, right? Does that mean I see 5 unique signals in the NMR? No, it doesn't. Okay. We see 4. Why don't we see 5?
Because it doesn't know those two.
The difference between the black and the purple was so subtle that our magnet didn't pick it up. If I wanted to see that 5th hydrogen, what would I use? A stronger magnet. Most of the spectra you deal with, that difference between those diastereotopic positions isn't enough for the magnet to actually detect. So it actually turns into one signal. Okay? And this is a challenging thing. If you are given the spectra, you interpret the spectra. If you're given the structure, you don't guess what the spectra is on it. You interpret the structure and say, this is what it has. Does that make sense? Okay. That becomes a difficult question to ask, right? So of course I would ask that like 10 times on the test. Those of you being like, yes, you would. You're not super nice. Do I need to worry about this diastereotopic mumbo jumbo with this structure? No, why not? There's no chiral atom. Most of the spectra you will see won't have chiral atoms because that is a more advanced level of thought. Right? Nobody took a deep breath and was like, oh, that's nice.
Thanks, Mike.
That should be nice. It's not, well, it's not really me, but okay. Okay, so just be aware that you should be counting hydrogens. So let's go through, take a look at this one. How many unique hydrogens do we see?
3.
Out of colors. Right? All those hydrogens. Are those all unique? Nope. Why not?
Those are the same environment, so in that same genre.
There's a line of symmetry across that molecule. These two are identical each other. These two are identical as each other, which means how many hydrogens do we have? 4 signals. Red, purple, blue, orange. Okay. The orange ones are still different than the red ones because
Yeah.
that oxygen. Does everybody see that line of symmetry and understand what I'm trying to draw on that? Okay, if you're one of those people that are like, I call BS, that's fine. Talk to me after class. Okay, because there's a subtle change to the structure that we can make to help clarify that.
Question. If the
After I
oxygen
deleted
wasn't there,
Yes?
then would it just be 2?
Okay, so it's a cool question. Let's get rid of the oxygen, assuming that you're leaving the methyl group.
Yeah.
How many signals do you get?
2,
Why 2?
because the hydrogens are bonded to both. Or close.
Line of symmetry. Line of symmetry, which means these hydrogens are the same as these ones. And this hydrogen is the same as that one and the same as that one, which means I only see 2 signals. Good question. So multiple lines of symmetry can just F with the whole system. That level of question is kind of an intermediate between full-on chiral and just counting hydrogens. We good? Good question. Okay. Chemical shift. Okay, the chemical shift is that relative local environment. What is it bonded to? I recommend that you memorize certain ranges. That's what's in my spec background file. Okay, there's a lot more ranges that are out there. You are welcome to memorize those if you want. The problem with memorizing those extra ranges, you usually overanalyze it and you screw it up. Okay? So I would recommend you simplify it. You're only using chemical shifts to memorize certain things. There is one kind of exception to that I want to throw on right here. How many different hydrogens do we see for the first structure? 3. 1, 2, 3. Yes? How many different hydrogens do we see for the next structure? Still 3. 1, 2, 3. Okay. So there's still 3 hydrogens in each of these. There's 1, 2, 3. Switch the other one. 1, 2, 3. I've also kind of color-coded this. This is a red CH3. That's a red CH3, yeah? Purple CH2, purple CH2, orange CH3, orange CH3. Okay, the reason I'm bringing this up in the chemical shift range and not further on down the line is if you move further on down the line, look at integration, how many hydrogens there are. Look at how many neighbors there are. You will find that for these 2 compounds, they're the same. They have the same number of signals, they have the same integration patterns, and they have the same neighbors. How do you tell them apart in the spectra?
For the chemical shift is on a certain.
The chemical shift is what's going to change. The closer you are to an electronegative element, the further you shift. In that first structure, this CH2 is right next to the oxygen, which means that CH2 should show up furthest downfield. When I move to the other compound, what's directly next to the oxygen? The CH3. Whoops, meant the red pen. Which means for that second structure, the CH3 should show up furthest downfield. So you have to be able to differentiate these 2 compounds based solely off of the chemical shifts. I don't agree with that, but that is how it is commonly tested. Okay? So I want you to be aware of that. Add an extra little wrinkle to this. Do I tell you to memorize where your hydrogen is if it's bonded to a carbon that's bonded to an oxygen? That's not something I think is worth memorizing. Okay? Even though I know it tests like that. It's not worth the effort. Okay? So be aware chemical shift can have a really big impact in your answer, and it can allow you to differentiate structures. In particular, it allows you to differentiate ethers.
So what would a question,
Or esters, sorry.
if we were to be asked a question, what would like the form of the question be?
Given the spectra like this is a crude spectra. Which of these compounds belongs to that spectrum? Well, you'd look at the spectra. The 2H is furthest downfield, which means the 2H needs to be closest to the oxygen. Where is there a 2H closest to an oxygen? The first one is closest to the oxygen. That's why it's there. Make sense? Okay. I believe there are questions like that actually in the practice exam. So you should be able to stumble across those. So chemical shifts, these are the ranges that I suggest that you memorize. It is up to you to decide that. You want to memorize more, that's cool, but those are the ranges I would memorize. Okay. Usually someone points it out, so I'll just point it out ahead of time. There's this weird kind of dead zone here that I didn't label anything. That's the everything else range. Okay. Again, it's not that it's not useful, and it's not that nothing shows up there. Stuff shows up there. But it's too easy to overanalyze it. Okay, so I don't bother to memorize anything in that spot because it could belong to 6 different things. And that's being kind. It's probably closer to 2 or 3 dozen different things. Okay, so I avoid any analysis that deals with those ranges. Okay? Which if you've been watching the SPECT org or the SPECT videos, hopefully you have, that analysis comes in as a question mark. I just don't know what it is, so I write a question mark. Okay? Don't be afraid to acknowledge that you don't know. keep moving through to see if you can get more information to help clarify. Okay. Integration is the ratio of hydrogens. So when we look at this spectra, do you see any integration information? No. Okay. That's because this is a digital spectra, and digital spectra, when pulled from the internet, oftentimes don't actually show the integration information easily. Okay? This is how ACS presents it. You're kind of expected to be able to interpret this. What they're expecting you to do is to look at the height of those peaks. Why could we use the height of those peaks to come up with an interpretation? Look at their widths of each of those peaks. They're all almost the same, which means the height can be used to interpret. Okay? We have to recognize, though, that these are three different distinct signals. So when we're talking about height, it's not the height of just the tallest one, it's actually stacking these on top of each other, okay, and trying to evaluate that process out. Okay? So you are very approximately estimating what goes on with it. For my approximative skills, I would call this 2H, 2H, and 3H. For those being like, where the hell did you come up with those numbers? Practice. That's all I got. Okay. I think that's a bit silly because I think that information should be given to you because the technology gives it to you. Okay. So it's dumb to just make you look at a spectra like this. Okay. How does the technology give it to you? Okay. What you would do on the computer is you would just select those peaks and say integrate, and it spits out a number. 2,123. Okay, as soon as you do that, you can then select these other peaks, and it's now going to spit out another number. 2,000, 0, 0. Yeah, my office is next to a math person. She would hate every time I say I don't like math. And I like math. Also, she wouldn't like that I say I'm not good at it, but whatever. 3,142. So it would spit out these big numbers, right? It's a ratio, which means divide. Divide by what? The smallest, just like you did with empirical formulas back in 151, all that fun jazz. That's what you would do here. Okay? With our instruments, it's actually even better than that, because it could give you those goofy numbers, but you could also go through and just say, make this 1. Okay? So it will then tell you, well, this one's 1, and this one is 1.5. What does that mean? 1 was a bad guess. Call that 2, and that becomes 3. Okay? So it would tell you that information, and it's usually reported at the bottom of your spectra. Other ways it can be reported, as you've seen in the packet, you'll see it written as 2H, 2H, 3H. What am I trying to tell you? I'm trying to give you that ratio information by writing it next to each set of peaks. Okay? Last exciting way that it could be given to you, which is super awesome. Just pretend. What that is the actual integration. It's just graphically depicting it. The integration spiked there. There was an area underneath the curve. So it spiked. That happens to correspond to the area under this one. This one, fudge, that was purple, is this one. This one is that one. So now what can you do? Old school, you pull out a ruler and be like, well, this was 10 inches. This was 3.5 inches. This was 3.5 inches. You now have a ratio. The last old school method, someone actually told me about, you printed it out, you got out a straight razor, and you cut the peaks out of the paper, and then you weighed the paper. It's pretty hardcore. Okay. But you get an integration the same way. It gives you the ratio of hydrogens. Let's see, do I have a spectra? Whoop, nope, we just kind of said Say make life miserable and jump straight to multiplicity. So in this structure, we said there were two hydrogens, right? The CH3 and then this H. What is the ratio that I would get from this compound? So number one, I get two signals, right? Okay. How many are purple hydrogens? There are four. Remember the lines of symmetry within this. It's the same as here, and because these are the same, so are these. There's four. How many blue hydrogens? 6, because it reflects across. If you were told 4 to 6, someone was being really nice. More than likely, what would you be told? 2 to 3. Okay, the integration is almost always the reduced ratio. If you're given something that's higher than the reduced ratio, we're really trying to heavily-handedly hint that that's actually the number of hydrogens. Everybody understand where that came from now? Cool. And now we should just all close our eyes and hope. Multiplicity. Okay. Hydrogens are magnets. So we stick my hydrogen sample and I put it in the large magnet and I mess with it and I see how long it takes to relax back. Okay. If there's electrons around it, that shields it, and I see all those little effects, right? Okay. But what happens if I have another hydrogen near that first hydrogen? Well, they're both magnets, right? Would those magnets affect each other? Yes. Okay. Would they affect each other if they were on opposite sides of the room? No. They have to be close enough to each other to have an effect. Okay. So what does that effect do? So let's go through and come up with kind of an idea. So here we go. We'll keep it really simple. There's our black hydrogen. It generates a signal. Okay, that signal is because it aligns with the magnetic field, right? Okay. If it has a neighbor, so we'll call it that red hydrogen could have aligned with the magnetic field, right?
Yes.
Did it have to align with the magnetic field?
It would have been on the other side.
It could have gone the other direction, right? Okay. Well, did the black one have to align up? No. How could it have aligned? Down. And then the red one could have been up. Black one down and the red one down. Now think about magnitudes, not signs, magnitudes. This is 2 going the same direction. This is 2 going opposite directions, right? Upper right-hand corner, what is that one doing? Those are going opposite directions. So the same as the bottom one, right? So those are actually partnered with each other. And the other one? So when I look at all the possible ways that these magnets could have aligned with or without each other, I end up with 2 possible states, where they both aligned the same direction or they aligned opposite directions. 2 possible states means 2 peaks. And this is where I'm trying to be very careful with the language and shift away from signals, because the signal is hydrogen, that black hydrogen. But this red hydrogen can now affect that black hydrogen by either kind of adding to its signal or subtracting from its signal. So when I look at all of those possible combinations, I get 2 ways that could come out. And I get 2 peaks. Each of those peaks has 2 possible sets within it, so each peak is of equal intensity. If I have one neighbor, I get 2 peaks. There's the boxes. Each of those peaks has the same intensity. Okay? Well, what happens if instead of having one neighbor, it had 2 neighbors? could have aligned up, 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 down, up. You get a whole lot more options, right? Draw them all out and guess what you find. There will be 3 possible ways it could have aligned. In those 3 possible sets, you will find that one of those sets had twice as many options as the other 2. And you get 3 peaks. One of 1 intensity, 1 signal, twice the intensity, and then 1 the same intensity. What happens if you have 3 neighbors? You go through all your possible sets, and guess what happens? 1 to 3 to 3 to 1. So the numbers in those boxes are representing the intensity, how tall the peak is. Okay? The box itself is representing how many peaks there are. When we look at this, they are all symmetric. 1 peak by definition is symmetric. It's symmetric with itself. If I have 2 peaks of equal intensity, they're equal, so it's symmetric. This one tall, short, tall, short. Short, tall, tall, short. Short, tall, taller. Tall, short. Thank you. Okay? So the peak patterning, when we're looking at multiplicity, is coming from that peak number and shape based off of your neighbors. Okay? And it will always be symmetric. So we can use this. If I see an overlapping of signals and it doesn't look symmetric, that's now a tip-off that what I'm looking at isn't 1 signal, but 2 signals mixing with each other. Okay? Just like it could happen in IR. Okay? What defines close enough? That close enough is the 3-bond rule. 3-bond recommendation is a little bit better. Okay? Unequivalent hydrogens are neighbors if they are within 3 bonds. Okay? If we think about how this actually gets referenced out, if you've watched other videos, they say it has to be 3 bonds. No, it has to be within 3 bonds. If it was within 3 bonds, so H, there's carbon, so that's 1 bond. We looked at the other one, there was 2, there was a hydrogen, so that was 3, right? That was 3 bonds. Could it have been just 1 bond? If it was just 1 bond, we'd have that. No, that's stupid, that doesn't work. Could it have been 2 bonds? Aren't those hydrogens the same as each other, though? Depends. Are the black hydrogen and the red hydrogen the same as each other anymore? No, they're connected to the exact same carbon, but they are now different from each other. Why are they different? One is closer to the chlorine, the other one is closer to the methyl. And because that is a pi bond, it can't rotate to allow those to exchange their relative positions to those. Which means you can encounter systems where hydrogens are connected to the exact same carbon but are neighbors to each other. You ever had that one roommate, you're like, I just don't want to talk to you? There you go. Okay? That's what's happening. Okay? So be careful of that within statement. Typically, 3 bonds. Okay? So this is what's getting us that patterning. So it allows us to predict what's next to the signal that we're discussing. That gets us some more information that we can build a structure on that allows us to get a little bit more detail and nuance out of our structure. That's why it becomes more challenging, because you have to know all of these pieces and all of those kind of subtle, crappy things.
What is this 1, 3 to 4 mean? Is that like when they mix together?
So the one, the 1 to 3 to 4, is that what you're asking? That's because I stole this peak or this picture from its origin. Anybody recognize what that is? I think it's Pascal's triangle. Okay? And Pascal's triangle builds this patterning. So if you're trying to figure out what goes underneath it, okay, well, those two things underneath have to be a repeat of above. So it's where they intersect, how it stacks out. Okay? So you can predict by adding. So if I take these two 3s, what intersects directly underneath it? 6. If I took the 4 and the 6 here, what intersects underneath it? 10. Okay? So you could predict this pattern out forever. Okay? We run into natural limits because it's hard to get more than 4 neighbors because
Carbon.
we've got carbon. And really it's hard to get beyond, I think 6 doesn't really work. Beyond 5, it becomes a little bit challenging to get more than 5 neighbors. Okay? It can happen, but it becomes harder and harder and harder to get more neighbors in there. Okay? So let's see, do I get a nice picture? So let's look at the splitting pattern. Let's keep it simple first. Right? We had 4 types. Keep it simple. Yeah? Let's take a look at that red hydrogen. Okay, so first and foremost, it should integrate to 3. So I should say a 3H signal for it, right? Why?
They're all the same.
I only see 1 hydrogen drawn.
The rest are implied.
You have to remember the implied ones. Okay. What should its splitting pattern be? So 1, 2. Is that a neighbor? No, why not?
Same house.
Chemically identical. Careful with the same house. We talked about that. Okay, so they're chemically identical. There's no way I would confuse those two with each other, so that doesn't count as a neighbor. You're living in the same house. Okay, and still talking to them. So let's count the other direction. 1, we've got our 1 bond. There's 2, 3. Am I out of hydrogen now? Yes, so what does that mean?
The neighbors.
That blue one is now a neighbor, so I can call that one neighbor as blue. If we whoops, forgot what I was trying to do. I need this. Now let's count the other direction. 1, 2, 3. Am I out of hydrogen? No, so that doesn't count as a neighbor. 1, 2, 3. Am I out of hydrogen? No. 4, and I'm at that hydrogen. It's called the 3-bond rule. Don't make it 4. Okay? So how many neighbors do I have? 1. So 1 neighbor, how many peaks would that be? 2, and I get 2 peaks. Okay? That is oftentimes referred to as a doublet because there's 2 of them, double. Okay? Oh, that was a bad idea to switch to that color. 1 neighbor, 2 peaks, or a doublet. How many neighbors does the blue one have? 1, 2, 3. Yeah? So 1, 2, 3. Is that a new neighbor? It is chemically identical. Do you have the exact same relationship with everybody in the house that lives next to you? Okay, no. So it still affects the signal. It still counts as a neighbor, even though it's chemically identical. Okay, which means from the red ones, how many are we going to get? 3 neighbors. That's why I wanted to color code, and I need to knock it off. Okay, I only counted 1 direction. Could I count the other direction? 1, 2, 3. Am I out of hydrogen? Does that count as a neighbor? Yep. So 4 neighbors? Why 5? There's another implied hydrogen there that we have to remember. There are 5 neighbors for the blue one. 5 neighbors means
4 peaks. 5, 6 peaks.
6 peaks, which would be hextet, okay, or sextet, sorry, so that we don't confuse it with the hept, which is also awesome because we could confuse it with a singlet. Okay, so we call it a sextet. How about the purple ones? How many neighbors do they have?
2 neighbors.
4.
Why 4, not 2? I heard a lot of people say 2, and I'm going to guess because you're like, there's 1 and there's 2, right? So how many neighbors were there? 4 neighbors, which means 5 peaks, which means pentet. Yeah? Orange. 3 hydrogens. It only has those 2 as neighbors, which means we get, 3 peaks, which is a triplet. Remember, n plus 1 equals your number of peaks. Yay! So for those people being like, God, I hope I don't have to do that in a full solve. In a full solve, you'd be responsible for piecing that all together. That is challenging. So what I could ask on an exam, what is the splitting pattern expected for the hydrogens in the orange circle? Okay, what's the splitting pattern or the multiplicity? We have to know how many neighbors, so we would look to this and say that that has 2 hydrogen neighbors, which means 2 neighbors means 3 peaks. Okay, so we could write it out as 3 peaks. I could also write it as singlet, doublet, triplet, quartet, and you would identify a triplet. Make sense? That would be a multiple choice question. Yep. Okay. So I can, and this is where doing the spectra packet is useful, because it allows you to get all of the layers to combine all of those pieces. The multiple choice will be like, just do this one little piece for me. Okay. So it simplifies the amount of work that you have to go through. Kind of, sort of? Okay. Should we throw just a flippin' monkey wrench into that? Yes. Okay. So this is complex multiplicity. Splitting of splitting. It's what the title shows up here. I remember when we referenced this, we said that we had, where did it go? A purple hydrogen and a green hydrogen. That those 2 were different from each other because of the flippin' chiral atom. Yeah? Okay. So I want to simplify this argument, and I'm just going to delete. Actually, I can't just delete that. I'm going to go out here and make this a CCl3. Why would I make it a Cl? We're talking about splitting, and splitting is about neighbors, and in particular, neighboring hydrogens. By making it a Cl, what happened to my hydrogens? Gone, I don't have to worry about them. Okay? So now let's look at this hydrogen. The blue hydrogen. I want to know what its splitting pattern is. Okay? And we looked at it already. What did we say it was? Never mind. In the simple explanation, what would we say that blue hydrogen's splitting pattern would be? A triplet, because it has 2 neighbors. Everybody cool with that? Okay, because here comes the fan. That makes it sound like, yeah, never mind. Are the green and the purple the same? No. If our magnet is strong enough, it can differentiate those, which means they will each have a different effect on that blue hydrogen. So let's start it off. The blue hydrogen starts with a signal. Ta-da! Signal. That's a signal. It sees the green hydrogen. There is 1 green hydrogen neighbor, which means that signal needs to do what? Split into a doublet, 2 peaks. Right? Because it saw the green hydrogen's cool, right? So it saw that first, it splits into a doublet. Now it sees the purple one. So now it goes, oh crap, I got to split because I have another neighbor. The purple one is still just 1 neighbor, which means 2 peaks. But what's my signal look like right now? It's not a single peak right now. It's 2, which means what happens when it splits? It splits into an additional 2. That one on the left splits into a doublet. The one on the right splits into a doublet. What? Yes. That's known as splitting of splitting. Couple things to note here, which are going to be relevant here on the next slide. if we go through, the distance between those peaks is different than the distance between those peaks. Why?
Because you double signs.
It was a different split. Okay? That split was caused by a coupling between the blue hydrogen in the green versus the blue hydrogen in the purple, which means the signals split differently. I can quantify that, believe it or not, okay, to give me some information about where those things came from. Okay, but what we're looking at here is what's known as splitting of splitting. This would be known as a doublet of doublets. Not to be confused with what people call a doublet of doublets in the aromatic region. They're lying, it's not a doublet of doublets, that's two doublets. Two doublets means two different signals. This is two doublets where it is one signal. A doublet of doublets is one signal. Two doublets is two signals. A doublet of doublet is one signal that's split multiple times. Two doublets is two signals that each split into doublets.
Can you write that down?
No. Okay. So let's just throw caution to the wind. Sarah's already like, I'm sorry. You're not alone. Just realize that. You're not alone. I want to know the splitting pattern for that. Oof.
Double.
For that purple hydrogen now. Notice I threw in a chlorine to simplify this again. What would the splitting pattern be for that purple hydrogen? We'll start with the signal. There is a signal. Is green different from orange? Yes. Okay. So what do you think is going to happen?
Splits into a doublet in the green.
Purple sees green and it splits into
Doublet.
a doublet. And now it sees orange, which is three neighbors, which means four peaks.
Which is 6 total.
So each of those doublet peaks has to split into.
I'll just get it wrong.
Okay. What would we call this now? This is a doublet because there's two sets of quartets. Okay? It is a complex splitting pattern. You don't need to stress a lot about it, but I want you to be aware of it. Okay? Long distance splitting, I want you to be aware of this. Sometimes you can get 4 bonds away. It's usually involving a pi bond. Why would a pi bond involve long distance splitting? Pi bonds are shorter. It bridges that gap and brings the atoms just slightly close enough that it allows for that splitting to happen. So you can sometimes see long distance splitting. It is typically rare.
Would the hydrogens in a tert butyl be neighbors?
Made sense.
So I understand where you're going with that. So let's look at a tert butyl.
It's just a common.
They're all chemically.
Are they going to be neighbors to each other? Since they're all chemically identical, they aren't neighbors. They just total in as 9 hydrogen. Okay, so we talked about, okay, and I know, deep breath, sigh, let it sort of go, and because it's just going to make it worse. Okay, we talked about the how much they split. Okay, that how much they split is how closely those hydrogens are coupled to each other. So we can refer to the distance between those peaks as a coupling constant. Okay, why is that important? Well, if A is coupled to B, the distance between the peaks of B and the distance between the peaks of A is going to be equal to each other. So I can do fancy fun calculations to figure out what that coupling constant is, and I can tell you that A and B are splitting each other. If I go through and look at C, notice C isn't being split by B or A. The coupling constant, the distance between the peaks in C, is 7.6 versus 8.5 versus 8.5. It's different. Why is it different? It's not coupled. But C is splitting D. Take a look at the signal for D. What's the distance? 7.6. So you can reference the distance between those tiny, tiny little tiny peaks to come up with coupling constants. It is usually exceptionally rare to deal with this. It usually involves just looking something up. Where it becomes relevant is not in our general structures, but in something along these lines. If I were to look at all of the stuff we have addressed, what is the difference between these two structures as far as spectroscopy goes? As far as spectroscopy goes, same chemical shift, same atom connectivity, same neighbors. All of those things stack out being the same. How would I be able to differentiate those? Well, one fun answer would be, you don't. Sorry. You do, because these hydrogens have changed their distance from each other, which means their coupling has changed. So if you can determine what that coupling constant is, you can look up a table to see that difference. When they're cis, that coupling constant is between 7 and 12. When they're trans, the coupling constant is 13 to 18. I want you to be aware of this. This is why I'm spending less than 5 minutes on this part. Okay? You would just look it up. It is something in the smart work because I want you to have experience with looking it up. I would never ask a test question on it because it requires that you have to do a bunch of calculations. And if I don't want to do those calculations, then,
You don't want to do it.
well, it's not that you probably didn't want to do most of this class, and I'm still going to make you do that. Okay? But that, believe it or not, is the end of NMR. Where we're going to pick up with on Monday is looking at UV, Vis, and IR. Yes, they are on the test. They're on the test at very simple levels. Remember, we talked about IR earlier in the semester as far as the lab went, and I told everybody in lecture, you should be looking at this. If you've done so, the IR should be relatively straightforward. The explanation for IR, the little kid box with the shapes, that's what you're doing. Shove the square in the square hole. Okay? And that's roughly how fast it should be. Okay? The square fit in the I'm done. That's how IR goes. Okay? There are things that you should memorize. I'll flip to that in a second. UV Vis, we'll talk about. It brings in the reality of molecular orbital theory. I'm just going to slide real quickly. I know. Whoa. 2 slides on IR that I highly encourage you to look at and evaluate. That sheet that you've got, I'm going to steal it, that has some memorization stuff on it from the tutoring center, it should look familiar because it's mine. Okay? Because they asked for something and this is what I gave them. You shouldn't ask for things. Okay? So that's where it came from. The IR thing up there, I just stole from the internet because it had most of the stuff in it and it was formatted pretty. This isn't formatted pretty. Okay? These things are what you should memorize, minimal for IR. This is bare minimum. This is like 60 to 70% of your grade, right? On IR. Just the IR section. You should know those ranges. It's not just bond to frequency. It's also knowing what it looks like. That comes from practice. That's cool, but if you really want to top it off, that's where I would move to the BA list. I'll let you be creative and figure out what that is. The BA list is now looking at some slight nuances behind those and what they're actually referencing. Okay? So with that, I apologize. I'm done.